Last time we have discussed about sub-threshold current, right? And today we are going to discuss about the backgate bias effects. Right. Backgate bias effects. Backgate bias effects. We have to think about this because in actual circuits, okay, in actual circuits, for example, we can imagine the circuits, for example, something like this, transistor 1, transistor 2, right? And then this may connect it to other transistors like a T3, something like this, okay? And this is the ground. And T2, in this situation, T2 is different with such a bias comparing to T1 and T3. It's a different situation, different substrate bias. So this T1 and T3 will behave differently from T2 because it has a different substrate bias. So we have to think how much the backgate bias affects on the transistor functions. Neglecting geometry, the threshold voltages, we have discussed that the threshold voltages is going to be the work function difference from the gate and the semiconductor, and the fixed charge part, and then the flipping potential with 2q epsilon Na. This we have done, right? Plus V sub over C naught. And here what we are going to do to identify the backgate bias. This backgate bias is nothing but as VSB that we have discussed in this equation, right? So we can rewrite this equation as threshold voltage. Now C naught phi f plus 2 phi f plus C naught over 2q Na 2 phi f and plus 2q Na 2 phi f plus result over C naught. And now we want to take this thing out. 2q Na to phi f over C naught. Okay, if you look at this equation, you can see that we add this term and take that term out later, right? And this is this can be expressed as a TH naught, and obviously TH naught is this equation, and then you can see that Q, oops, to phi f plus phi sub minus square root 2 phi f. So obviously this part up to here, this part is we set threshold voltage VTH naught, right? And then we factor out this term like this, and then we want to call this delta VTH. So this is the part coming from the substrate bias V sub SB, right? So in this expression, we can see VTH naught as the threshold voltage with the substrate bias at the source potential. And if we plot, there is experimental data in the reference, but if you plot the VTH, delta VTH, which is a correction factor coming from the backgate bias, and then you plot it with respect to the substrate bias, okay? Then we have a curve something like this, 2, 3, for example. This is a rough figure, right? K1 is equal to 2.0, and K1 is equal to 1.0, and K1 is equal to 0.25, where the K1 is SNA over C naught, and delta VTH is going to be K1 2 phi f plus reserve minus 2 phi f. Okay? And you can see that the K1 is equal to 2.0, where T oxide thickness, gate oxide thickness of the MS transistor is 1500 angstrom, and then substrate doping level is 0.0 ohm centimeter, corresponding to the 0.9 ohm centimeter. Okay, and this is the equivalent K values you can have when the oxide thickness, if you reduce the oxide thickness to 1000 angstrom, then Na corresponding to 0.4 ohm centimeter. You slightly increase the concentration of the substrate, okay? And in this situation, you can have a same K1 value, which is a 2.0, and with the substrate bias, you can see the tremendous change in the delta VH. Okay, so this is not a good condition, as a matter of fact. The transistor is going to behave, change a lot. The threshold voltage is going to change a lot from the VTH naught, because with increasing the substrate bias. You can reduce these factors by set the same oxide thickness and the substrate. You can reduce the substrate doping like 34 ohm centimeter, which is you reduce the substrate doping, okay? Or if you keep the oxide thickness at 1000 angstrom, in this case you can have substrate doping like 24 ohm centimeter, corresponding to the 24 ohm centimeter. Then the K1 value is going to be 0.25, and then with the substrate bias, this transistor is not going to change a lot in terms of delta VTH, right? So you want to have a transistor something like this rather than something like this. So, as I drew before, if you have a transistors like this kind of transistors, if you have, and this transistor, if this transistor T1 and T3, it has a different substrate bias from the T2, and if the transistor has this properties, which means these transistors is going to change, threshold voltage is going to change a lot with respect to the free substrate bias, then the threshold voltages of T1 and threshold voltages of T3 is very much different from the T2, because the substrate bias for the T2 is different from that for T1 and the T3. So you don't want this kind of a process, fabrication process. You want to maintain the transistors in this low value of K1. Okay. So that means you want to have a high resistivity substrate, and you want to keep the oxide thickness as thin as possible. In other words, to minimize the delta TH values, okay? What you have to do is you have to first the high resistive substrate, and thin oxide, thin gate oxide. This is what you want to minimize the backgate bias effects. However, ideal scaling, we are going to talk about this ideal scaling later in this class. It says you should use heavy doping. It's preferable. Right? So, to compromise, what you can do in an actual process, you can have a transistors, for example, P sub, okay, and then here's the N plus, and then you're going to channel stop implant, P plus, P plus, this is the field oxide, okay, and this is the channel stop implant. Then you have a gate here, which is going to set it on top of the gate oxide there. And then what you can do is you can have an implant so that use high resistive substrate, but in order to have a good position in the ideal scaling, you are going to implant channel to correct threshold voltage. So use a high resistance of a substrate to minimize the delta VTH that we have discussed right now. But if you use a high resistive substrate, then the threshold voltages is not going to be maintained to the values what you want, so that you are going to implant the channel area. We call that threshold implant. Threshold implant to control the threshold voltages. Then we can use the high resistive substrate to minimize the backgate bias here. So that is a compromise. And as far as the device functions is concerned, you have to have another compromise for the implantation of the channels, which is going to discuss about the substrate resistivity selection and next section. And before that, let me just finish this section by showing the experimental data which V subs and threshold voltages. Okay, this is threshold voltages including the body effect, and this is the body substrate, right? The body bias, potential that we apply. And when, say, oxide thickness is about 200 angstrom, and this is the typical values for the MOS device, and the substrate doping level is 2.5 times 10 to the 16. This is the very normal values, and if you set these values equal to the channel implant, which means, the threshold implant, which means you actually do not do any threshold implant to compromise the situation, okay? Then threshold voltage and the VSO is going to change something like this. It's 0.5, and this is a substrate bias at 1, 2, 3, 4, something like that. Now, if you do if you increase the oxide thickness to 350 angstrom and the substrate doping level like 2.5 times 10 to the 16th, it's the same to this situation, and you are not doing any threshold implant to correct the threshold voltages, and then threshold voltage is going to change something like this. Okay, just to increase the gate oxide, and this value is about 2.3 something, somewhere there. Okay, this is a 0.5. Now, if you do the threshold implant to control the threshold voltages, now what you can have is, if it is a 0.6, threshold voltages is going to change something like this. And this is the situation where you are going to have a same gate oxide there, and then doping level is 7.5 times 10 to the 16th. But you are doing the threshold implant so that the 4 times 10 to the 16th. Okay? And the D is about 0.2 micron. D means the channel depth. Here is this depth after the implantation on top of the 350 gate oxide. Okay? Then you can see the body effect can be minimized with this extra implant. Okay, so that's how we can compromise, minimize the delta VH, the effect of backgate bias on the threshold voltages. Now, I just mentioned that we have to do the another compromise to have a better function of the MOS device, which is the resistivity selections. What kind of materials to begin with? If you want to set up the MOS, for example, you start out with the P-type substrate, and then this P-type substrate, the doping has to be done on the Czochralski growing to wafer preparation. It has been done during the wafer preparation, right? And this, what is the doping level should be to have a reasonable device to be built on that wafer. It may be regarded trivial, but because we have a good point and bad point to have a high resistivity materials, it is not a trivial question at all. It is very important to compromise between these two effects, doping levels, I mean. So if the doping level is high, then we can have this benefit. Firstly, less DIBL. DIBL is nothing but the geometry effects. Okay, drain voltage effect, something like that. DIBL is drain induced barrier lowering. It is a different interpretation of the physical processes happens after the increasing the drain voltages, or if you have a small geometry, then we can have a very similar situation to the drain increasing the drain voltages. And we also this DIBL phenomenon can be thought the effective channel length reduction things. Okay, so we are not going to discuss about the DIBL in detail, but it's the same phenomenon that we are going to discuss in a small geometry and high drain voltages sections. So we are going to discuss about that. So we are not going to discuss about the DIBL phenomenon separately. Anyway, this we have. If you have a high doping, then we can have less DIBL, which is good, and less delta VTH body body effect, right? Beckett bias effect with length geometry, length and the W, the width of the channel, and then drain voltages. Okay. And it is beneficial in ideal scaling. We are going to discuss about this ideal scaling later. But anyway, if we have a high resistive material, then we can have the benefits. On the other hand, if we have low resistive substrate, then low junction capacitance, and that is good point. And threshold voltage becomes independent of Na. Okay, the substrate doping is not that sensitive. The threshold voltage becomes not sensitive to the doping, and better sub-threshold slopes, which means we have a good switching properties. Okay, and then finally we have a better backgate bias sensitivity. These are all good points by having a low resistive substrate. So we have to compromise between these two, right? And the experimental data says substrate resistivity and this is the threshold voltages, and then you can see the zero threshold voltage is somewhere around here, and then plus 6 is here, and then it's far bigger than that. If you have oxide thickness is about 0.1 micron, it's 1,000 angstrom, then the threshold voltages is going to change something like this. And then this value is about the substrate resistivity is about the 4 ohm centimeter. Okay, this is a low scale. And here, let's say this is about the 100 ohm centimeter, something like that. Now, if you increase the oxide thickness to the 1 micron, then threshold voltages is going to change something like this with the substrate doping level, substrate resistivity. And for this, it is an MOS device, and the fixed charge is about 5 times 10 to the 10, and along 100. Metal work function is about 0.6. Aluminum or anti-poly gate, and the threshold voltage is calculated on the discussions that we had. Phi f plus Q Na 2 phi f over C naught, okay, where the QF is Na over Ni, okay. So in this experimental data, we can see that, note, if resistivity is greater than 2 ohm centimeter, then threshold voltage becomes 0, and so implant can easily control threshold voltages independent of substrate resistivity. So for the body effect, if you take into account of the body effects and this substrate selection, substrate resistivity effect, now you can compromise the channel something like this, okay? You first start out with the high resistive substrate. Now this is the M plus and M plus, and then the channel stop implant is going to be done right beneath the field oxide, something like this. Okay, and then now you have two kinds of compromise has to be done, and for one is for the delta VH minimization, and the other is the high resistive selection. And all this is for control the threshold voltage, to have a correct threshold voltages with a high resistive substrate, right? So this compromise can be summarized like a high resistive substrate, and this high resistive substrate will give you low capacitance, threshold voltage makes independent of substrate doping, and good backgate bias sensitivity. Right? And you are going to do the P implant. A channel. It's just a doped surface. To get desired threshold voltage and improve DIBL things. Right? Well, the next topic that you have to discuss is about the velocity saturation in MOS devices. Okay. So far we have discussed about general MOS device operation, right? Operation. And here we are talking about the accumulation and the depletion and inversion. And for here we have discussed about the threshold voltages and IV curve. Okay, and then especially the drain current can be modeled like geometric vector, and we call this, we lump all these things to the gamma in our class node, and then Vg minus Vth minus Vd over 2 Vd. And that is the source and drain current before saturation, right? Before saturation. And ID becomes this gamma times Vg minus Vth square after saturation. So so the plot is going to be IDS Vg, and typically it's going to show something like this, and this is saturation and before saturation. You can distinguish those two parts, and you can draw some lines here before the saturation and after saturation, something like this, right? And then this is a pinch off point where you can see that saturation of ID drain current is defined when Vd saturation drain voltage is exactly the same to the gate voltage minus threshold voltages. This is nothing but to say when the surface potential near the drain no longer support an inversion layer. Okay, that is the saturation. And physically, what we can see at this saturation is that we have a source and drain, and the inversion layer now becomes somewhere something like this on the gate, and this is the inversion layer, and we call this as a pinch-off point. Okay, and then at this point, the drain voltage is gate voltage minus threshold voltage becomes a drain voltage right at here. Okay, and the most important thing happens with this pinch off is that we have a new channel length. Okay, that is the a very important point to notice. So that means the average electric field between source and drain now is going to be average is going to be threshold voltage and gate voltage. And now you have to use a new length between source and drains, because the inversion layer, all the charges in the inversion layer is going to be confined physically in this new effective length. So in other words, your electric field between source and drain becomes large, right? Becomes large when you increase the drain voltages. So if you take this thing into account, then the device function is different what you can expect from the simple model, MOS models that you had before. So if now gate voltages and threshold voltage becomes the same, threshold voltage is 3 volts and effective length is 1 micron, then the electric field, average electric field, now becomes 3 volt per micron, which is 10 to the 4 volts per centimeter. This is a pretty high value. If you compare that electric field with the general electric appliances, then this 3 times 10 to 4 is not a low electric field. It's a pretty high electric field. And with this electric field, we can draw the velocity of electrons and the electric field, for example. Now, you see, it's linearly proportional up to some values. We call that the critical electric field. And this slope is correspond to the mobility, the material constant, right? But if you enhance the electric field beyond this critical electric field, then it's going to deviate from the straight line, something like this, so that you are not going to have a constant mobilities of the materials. So now the drain current is directly proportional to the mobilities of the electrons and holes at the channel, and most of the current is going to flow along the surface, the interface, okay, surface. In the MOS transistors. The velocity saturation is very important and very sensitive issues in the MOS transistors because of this surface scattering. Okay, surface scattering. That is at least 2 or 3 times bigger than the bulk scattering. So this mobility issues and the critical electric field, most of the MOS devices is operating under beyond the critical electric field because of the geometry of the device. The device is so small, and then the drain voltage is high enough to get a pinch off during the channels, so that we are going to have a new value, L effective values, which is very much less than L effective is also very much less than the designed length of the gate. So next on Wednesday, we're going to discuss about this velocity saturation and other things and related to the MS characteristic. And the next week we're going to discuss about the Chap phenomenon, which is inevitable in the CMOS recent CMOS devices. Okay, I'll see you on Wednesday then.